Okay. All right, so my plan for this second lecture is to finish this mapping onto a statistical mechanics model for random tensor networks, and I'll discuss precisely what goes on at the boundary and finish this mapping and tell you about how in some cases it can help us actually compute critical exponents and so on. And so I'll spend probably most of the lecture doing this, and so, but in the end, I'll switch to the MBL transition, and I'll try to say a few words about the MBL transition, and I think we'll hear more this afternoon. But so I have put some references here about the MBL transition. I'll get back to this. I have only put renormalization group type toy models. There are many papers on the MBL transition, both numericals and theory. So I have focused here on toy renormalization group models, and I'll get to this, hopefully, once I'm done with the measurement transition. All right, so what I showed before the break is that, so I focused on those random tensor networks, and like I said, the same more or less applies to the measurement transition, although the model is a bit more complicated. And so what I've shown is that the average Rényi entropy can be written in the following way as a limit of a free energy difference. So you can think of it as a free energy cost, and you'll see those two free energies will differ only at the boundary, where F is minus log Z. And so what I showed is that if you focus on Z naught, so Z naught is just trace of rho to the n to the m. So it's this thing where you don't do the partial trace. So this ends up having the form of a partition function in the following way. So you have permutations. So those are like your spins, if you want, of that StatMech model. And so they live on sites. So remember I had like a square lattice. So each permutation lives on a site. And so those permutations live in SQ, where Q is the permutation group of, SQ is the permutation group of Q colors, and Q is n times m. And so the weight that you get is a product over all bonds on that square lattice. And what I argued is that this weight is d to the power of this function I call chi. And so chi is an integer, and then permutation or representation theory of this group, it's known as the number of cycles in, so chi of G is the number of cycles in a permutation G. So let me define this a bit more precisely. So say you have like, I don't know, again, you have 4 replicas. So a permutation you could draw in this way, right? Say you permute those two, and maybe those two are not changed. 1, 2, 3, 4. So that's a given permutation. Okay. So this would have 3 cycles. Okay, and so the way you see this is you go from 1 to 2, then 2 to 1, and this closes. Okay. So you can kind of form loops if you want. Okay. Okay. So this would like, so if I draw like this permutation here, this chi of this G, this is G as a permutation of S4. This has 3 cycles. So just an example of what the number of cycles is. So it's a well-defined quantity. It's an integer, positive. And again, it's a class function, so it has this property that it's the number of cycles. You can easily convince yourself that if you multiply by any permutation on the left and on the right by h minus 1 gh, like conjugate, this is the same thing as the number of cycles in G. Okay, so that's what I showed. Okay, so I haven't really argued why it factorizes on 2 bonds, but that's very easy to show. Okay. So each permutation is like this contraction in the Wick theorem, and this is basically just summing over all the degrees of freedom left. Okay, that's how you get this number of cycles. So, all right, so it's a relatively like ugly looking thing, right? But the nice thing about it is like you can think of it as a partition function, right? So Again, those are like degrees of freedom. They're my spin, and this you can write as exponential of log d, sum over nearest neighbors of this chi of gi minus 1 gj. Okay, so you can think of it as minus your Hamiltonian. So it's absolutely like a legit statistical mechanics models. All my Boltzmann weights are positive. Okay. So if q equals 2, you can easily show this is an Ising model. Okay, there's not that many StatMech model with 2 degrees of freedom. Okay, but if q is 2D, so it leaves classical 2D. Okay. No, sorry, q here is n times m, so it's number of replicas. Right, so it's n, so yeah, let me remind you, so n is my Rényi index. So I have 2 replica indices here, so one n is Rényi index, and m is this artificial replica label I added just to make this work. Okay. And so at the end of the day, I want to take m goes to 0, which obviously is a bit painful here, right? So I have this spin model for any q integer. I can definitely write this, do Monte Carlo, whatever. In some cases, compute this exactly. But at the end of the day, what you really care about is q goes to 0, which makes, yes, sorry. Yeah. That would be a bit sketchy. I think you want to take the other limit. Yeah, I think you want to take replica limit first and then take m into infinity. I would worry about this. Yeah, but I mean, you could maybe, but I'm not sure that would help you. And I would worry that's the wrong order of limit. Okay, so that's what I showed. So again, it's kind of an ugly StatMech model, but it is a well-defined StatMech model. Okay, it has weights positive and so on. Okay, so now I need to tell you what goes on at the boundary. So in particular here, I've computed Z naught, okay, and it looks like so it's a 2D classical StatMech on the square lattice. So this is on the square lattice. So now I need to tell you about what's the difference between ZA and Z naught. And so it turns out those two only differ at the boundary of my system, which is maybe kind of obvious by definition, right? I said the only things at the boundary would be different for those. So those differ at the boundary. And in particular, this is where we'll see this domain wall. And they'll have different boundary conditions if you want, okay? Okay, let's go back to our, so I said I had a square lattice. And let's imagine I have maybe periodic boundary condition in the spatial direction, and this goes to infinity. So that's the direction I call tau. And now I have physical legs. And let's say my Hilbert space here has dimension d. And my bond dimension is capital D. So, all right. So in Z naught, if you consider the boundary, if you consider this boundary more carefully, so you look at what those physical legs do. Okay? So I'm not going to do this mapping, but you can relatively easily show that basically having those degrees of freedom is like having a fixed permutation living here. So this will be like a boundary field. Okay? So so this I won't show. That each link I draw here, so this blue thing, you can think of it as a permutation, which is just the identity. And which is, in my notation, which is I just don't permute anything. And here I have a degree of freedom, I call it Gi. So each link like this will have a weight, now small d, which is this dimension of my Hilbert space, to the number of cycles in Gi. Okay. And so for Z naught, so that's Z naught. So you have uniform boundary condition with only this identity permutation. Okay, so intuitively what this is doing, this identity permutation is just doing the trace. Okay, so it's kind of implementing, you can convince yourself that this is the way you do the trace. So now the one that requires more care is like ZA. So what I call ZA is the one that has the partial trace. And now N and M are actually not equivalent, right? So it's very crucial. They play different roles, right? And so what happens in that StatMech model, let me reuse the same picture. So you have this interval A. So let's say that's A. And so in A, you'll have a different fixed permutation that will basically do the partial trace for you. So each red dot is a specific permutation that I'm going to call G swap. So let me draw it in pictures. So for each Reni, so it lives again in SQ. So what this does is for your Reni indices, it contracts each copy with the next one. So it's basically doing this partial trace. And then with static boundary conditions, so that's like n spins. And then you replicate this and do the same in each replica. Okay, what I'm saying here is not entirely obvious, and again, just in the sake of time, I won't show this. So if you're used to doing entanglement calculations, you probably won't be too surprised that this permutation shows up. It always shows up in entanglement calculation. Okay. So what this is doing, so now you have m copies. So it's basically a permutation. It does live in this SQ, right? So within each replica, like disorder, it does the same. And within each replica, it connects, replica 1 with replica 2 with replica 3, and then the last one with the first one. And what this does is actually doing this partial trace. You can convince yourself that's exactly what you need to do this partial trace. Yes? Oh, sorry. So it's connecting Reni replicas. Okay, so this is doing this partial trace for n. And then you have everything to the m, so you do the same in each. So it's just a specific permutation. So now my claim is that each bond here, okay, so every time I drew like a purple thing with this red thing, and now I have a GI, and now you have this G swap, whatever it is. It's a fixed thing, so you're not summing over this. It's like a fixed boundary condition, okay? And this link is D to the chi G, this whatever permutation, G swap inverse GI. So, okay, and so D is like my physical dimension of my Hilbert space at the boundary. Okay. So it sounds like complicated. What really you should think of these is they're like boundary fields. And so if you had like a Ising model, this is really what this would be. Like this identity would be like say spin up, and this G swap would be you swap things, so that would be spin down. Okay, so you have different boundary conditions. So in that StatMech model where you have like all those permutations, it's just more complicated. But like whenever you have blue, you have this identity permutation, and whenever you have red, you have another permutation that's fixed. So effectively, it's like having a boundary field in those StatMech model. So that's basically the end of the mapping. Okay, so I haven't shown this in detail, but you can easily convince yourself it's true. So from this, you have mapped exactly. There's no approximation here. Okay, the only thing that's really non-rigorous is taking this replica limit. But otherwise, everything is exact. This average, you can compute exactly as those partition functions with those things. So if you could compute those partition functions exactly, you'd have exactly your entanglement entropies. Okay, so let me now go back to the physical picture, right? So this was the technical part of showing this is true. Let me go back to what we can do with this, okay? So I mentioned that when D is large, okay, so let's say D goes to infinity, the bond dimension. So my StatMech model, you can see it's like going to very low temperature. So this is like T goes to 0 in the StatMech model. Okay, so you expect your StatMech model to order. So meaning it's a ferromagnetic phase. And so in particular, you can see that the coupling, you want to minimize the energy. Okay. And so the way, so you want to minimize the energy of your StatMech model, and the energy is just, each link, it's just minus this number of cycles. So you want to maximize the number of cycles. What it means, the way you maximize the number of cycles, so the permutation that has maximal number of cycles is just identity. It has as many cycles as species, okay? So what this does is force all the permutations to be the same. Okay, so you want this to be identity, which means that Gi is Gj. So that's what you expect of a ferromagnet. You want all your spins to be the same. So it's a ferromagnet, again. All spins are the same. And so actually exactly in that limit, let's compute Z0 and ZA. They're actually dominated by only one configuration each. So I can easily do this and show you what happens. So what happens when you take D to infinity is all spins want to be identity. Okay, so now I have like a thermodynamic limit. So I have my spins at the boundary are all fixed to blue identity. So, I want to be a ferromagnet, so I want all my spins to be the same. Okay, so I'm going to stop drawing blue dots now. But like you can imagine, it keeps going down. Okay, so on each side, I have only one permutation identity, and that's the one that minimizes the energy. So, okay, so now you can easily compute Z0 and ZA. Okay, so let's compute this ratio. So Z0 is a partition function with all bonds are identity, all spins are identity. Okay. And so ZA, the difference is I'm forcing those permutations to be different. So, okay, so this ratio is going to be basically the energy cost for each of those bonds that I'm crossing here. Okay. That's the only difference. So let's compute this. So now ZA over Z0 is D to the LA. So for each of those bonds, we'll have this. And so the energy cost is having this G swap minus chi of the identity. Okay, so this is true only when D goes to infinity. All I've done here is is a low temperature expansion. I've kept only the first term. So I have only one configuration in each. Again, Z0 is one configuration where all spins are identity, and ZA is the same, but all those spins are forced to be this G swap. So now the ratio is exactly what I wrote over there. Okay, so I subtract off this, which was in Z0, and now I have this G swap instead. All right, so D to the LA. So number of cycles in G swap. Okay. So you look at this, you see that each one of these is going to give you one cycle. So go from 1 to 2, 2 to 3, keep going. So that's one cycle. So you have n cycles, one per replica. Okay. The number of cycles in identity, that's just the number of spins I have. So that's Q, that's n times m. All right. So, okay, so it's a completely exact calculation from the StatMech model. I just want to show you we get something easy in that limit. Yep. So that's also D to the LA M1 minus n. So you notice now it's not symmetric between m and n, of course. That's because of this G swap. You're breaking it at the boundary. So, all right, so now let's plug this into our formula here. So you take, so this implies that Fa minus F0 is M1 minus N minus 1 log of D times LA. And so if you plug this in the formula over there, you see that all my Rényi entropies averaged end up being log of D times LA. So what I've shown here with this very simple calculation is you get what I told you would get. This is a volume law entanglement. It scales with LA. And moreover, this is actually the maximal entanglement you could get here. It has this log D factor. Okay? So this is only, again, when I took the limit D goes to infinity here. Okay, so I'm very infinitely deep in the ferromagnet. This is just to show you that this mapping makes sense. Right? So you can, so this result, I should say, was first in this paper by Hayden and Al. So that's actually the limit they considered first. They didn't use replicas. But you see, you can recover it easily here. Okay, so that's volume law scaling. It's actually maximal entanglement scaling here. If you take this tensor network, what I've shown using this replica mapping is that if you take the bond dimension to go to infinity, you get maximal entanglement, which maybe is kind of natural. I have so many layers, and I took D to infinity, so I get basically a wave function that's as entangled as it could be. So hopefully you see a bit how this mapping works from here. So now you can also do a high temperature expansion of this, which I'm not going to do. So you could do the other limit, where D goes to 1, and perturb around this. Okay, and you can easily show you have area law entanglement. Okay, so this would be, again, the paramagnetic phase. And here you have domain wall condensate if you want, and it's very easy to show delta F is just a constant. And in between, you have to have a transition. Those are like high temperature and low temperature expansion of this model. Okay. So one thing I should say, if those of you are more like high energy people, so this here, so in general, I took a square lattice, and that's why I have this. If you took a different lattice, so this curve would actually be just a domain wall that will try to minimize energy. So this will do a minimal cut in your tensor network. Okay, so that's what's known as minimal cut picture. Okay, and so the reason this actually was originally more of a high energy type setup is this mimics the Ryu-Takayanagi formula for ADS CFT. Like you go through the bulk and you take a minimal surface. Okay, so this is just this. Okay, so in that limit, what you get is a minimal cut in your tensor network. But as soon as D is not infinity, this domain wall starts fluctuating, okay, and you actually need to compute that free energy, and it won't be given by a minimal cut anymore. In particular, if you want like this, minimal cut picture will break down completely as you go through the phase transition. Yes, Maxime. Oh, so the reason I picked identity is because of the boundary condition, though. So at the boundary, all my spins are identity, so I picked one of the symmetry broken states. Okay, it's like I'm breaking the symmetry at the boundary. So this StatMech model, if you look at it, it has a SQ cross SQ symmetry. So it's left and right multiplication by SQ, by any permutation of SQ. So it has, it's not a POTS model, is one thing I should say. Okay, it's not POTS, it's more complicated than POTS. So the reason I chose one state is boundary condition, is all. Okay, it's like a ferromagnet, but at the boundary condition, you force all your spins to be up, so you just get the up. Any question about this? Yes. Also. Yeah. So those are independent numbers. So I took small d to be finite. That's like my physical Hilbert space at the boundary. It could be like 2 if you have qubits. Okay, yeah. No, it changes. Okay, so that's one thing I should say. Yes, so if you go away from those limits, this is not like the MBL transition or ETH or whatever. This goes smoothly to 0. In general, this is like LA divided by correlation length. And this goes like to 0 smoothly. So this is not like, there's no jump like in the MBL transition. Okay, so I'll actually talk about this. This is a very important point, yeah. Okay, so again, the main conclusion of this, going back to the big picture, is that at least in that random tensor network model, hopefully I've convinced you, you can do like completely rigorously without waving your hands, too much map this onto a statistical mechanics model, and you can understand those entanglement transition, which look quite complicated, to basically a standard paramagnet to ferromagnet transition in this stat Mech model. Okay. And you're computing the energy cost of a fluctuating domain wall at the boundary. And again, let me emphasize that you could do exactly the same for the measurement transition. It's just technically harder, so I could not do it on the board. I could, but I would have spent a lot more time. Okay. But that's the only difference, otherwise you get pretty much the same picture. Okay, so both for this, so that's the main message. So let me spend some time telling you about what are the remaining questions and what we don't know. Yes, Ben? That's right. Yeah. Right, so that was actually our first, that was actually our goal, right? So we wanted to find something that was that was basically building on random matrix theory, if you want, but was putting a bit more structure, so you would have some notion of a transition, so you could tune something. And we even considered versions where even this graph was not a square lattice, but was also a random graph. So you would even try to get rid of any information, right? So you try to make it as random as possible, but still you get a transition. But that's actually a feature that I think is good, because it probably tells you it's very universal. Okay, so, and it's why it also probably shows up in this measurement transition that looks apparently very different. Okay, so you basically have very little input, right? There's no Hamiltonian, there's no structure. The only thing you put is, and you still get a transition in this. So that was actually at least at the time, we saw this as a good feature, that it looked very universal somehow. Okay, so that's just a property of those random states I took in this way. So you could ask, why did I take a square lattice and not something else, though? I mean, okay, so that's a fair thing. And then we did random graphs, like I said. So this would be CFT coupled to random graph, fluctuating graphs, if you want. So that would change things. But right, so I don't know how to write a parent Hamiltonian, and if I could, it's probably not going to be local, right? So I mean, they have not so great features, right? So I should say they're not, okay. So one way now, I mean, we started with this random tensor network. Now the way I think about this is just another way to get this measurement transition, which sounds a lot more physical. We can, you just time evolve with the non-integrable model and make those local measurements, and this is basically doing the same type of transition, which I think is a bit more physical than this, right? But still, tensor networks are usually a good way to think about entanglement features, right? So, anything else? Okay, so I will conclude this part by telling you more about what's going on at the transition, right? So here I've done this mapping. So, okay, so what does that tell you about the transition? Well, it tells you lots of things just based on conformal invariance. But okay, so now you still have to identify this critical point and take this replica limit m goes to 0. And it turns out this is a very hard problem. At least it took us busy for a few years and we never managed to do this. But somehow we just wrote the paper. So let me tell you some things. Okay. So at criticality, so again, you have a 2D CFT. So let me go back to this thing. I said it had central charge 0. So how do I see this? Well, I see this because the partition function is trivial. Okay, so both my partition functions like ZA and Z0 are just 1 as m goes to 0. So those are completely trivial, boring partition function. The free energy is completely boring. However, correlation functions are highly non-trivial. Okay? And in particular, notice that I want to compute a specific derivative of this. Okay? So the fact that the free energy doesn't scale with system size immediately tells you the central charge has to be 0. So it's a general feature of the replica trick. For those of you who do replica trick a lot, you always get partition functions that are 1, and you always get, if you have a CFT, central charge 0. So just a few things. Those CFTs are notably hard. Okay, so in particular, they're non-unitary. We know very little about them. There's a few, like the n goes to 0 limit of the ON model and percolation, which I'm going to talk about, which we know about. But there's also very hard questions like the plateau transition in the integer quantum Hall effect, which people have tried to solve for many years and never really managed, okay? Which are in the same family, just 2D. It's a class of 2D CFT, which we don't know So they're also known as, they have properties where they have logarithms that show up in correlation functions. So they're also known as log CFTs, okay? Which I used to work on in another life. But so, but I won't talk about this, okay? But basically, it's a hard problem. So I will just write this. So it's not because it's a 2D CFT, we could think we know everything we want about 2D CFTs that we can solve this. Unfortunately, it's not the case. So the partition function is trivial, but the model is still hard. Okay, so however, in some limits, this ends up being simpler, and this is where I'm going to go back to this measurement transition. That's the final thing I'll say about this, and then I'll move on to the MBL transition. So if you do the measurement transition, you get a stat-mech model, I told you, but it's more complicated, except in some limits, okay, where it becomes easier. So let me go back to this measurement transition. So it's measurement-induced transition, so I make those measurements on this periodic system. So there's also a stat-mech model. I'm not going to do the derivation. And in general, it's harder. The reason it's harder is it's harder to average over unitaries than averaging over random tensors. Averaging over random tensors gives you a Vic theorem. Averaging over unitaries gives you like one-garden functions, if you know about this, and it gets uglier, but you can still do it. So however, there's one limit. Okay? If you take the Hilbert space, so I told you I had Q dits. My Hilbert space on site was C to the D. It turns out if you take this D to infinity limit, so it's like a large N limit if you want, the stat-mech model ends up being extremely simple. Okay, it simplifies a lot. Okay, so it's hard. However, you can show that if this happens, if D goes to infinity, the stat-mech model simplifies a lot. So let me write down the partition function. So in that limit for that measurement problem. So it's still a sum over permutations. For reasons I'm not going to talk about here, Q is not exactly n times m, it's n times m plus 1. I won't talk about why the plus 1. It comes from the measurement problem. But still, then you have weights. It's not number of cycles anymore. And so now it's expressed in terms of that parameter P, which is the probability to make measurements. And so at that limit, it looks like this. Okay, so it's only in that very specific limit. Otherwise, it's, again, a class function as well, just more complicated. And exactly in that limit, you can show this is true. And P is the probability to make measurements. Okay, so if you make a measurement here, you basically get a Boltzmann weight that's doing nothing. Or if you don't make a measurement, you just have a delta function that forces your spins to be the same. So the nice thing about this is that, okay, if you're a stat-mech person, you probably immediately recognize what this is. Okay, so this is actually the partition function of a Potts model. So the first thing you should notice is this has a much larger symmetry than the model I was writing before. Okay, so before I had like this class function, gi minus 1 gj, and I said this has an SQ cross SQ symmetry. So this actually has a much larger symmetry. So this only cares about whether the two permutations are the same or not. So the symmetry of this is actually SQ factorial. Is that clear to everyone? So the symmetry of that model, so I can even forget that those are permutations. I can just say they go from 1 to Q factorial, which is the size of SQ. Okay? And the Boltzmann weight only cares about whether they're the same or not. So this has a much larger symmetry compared to what I had before. And this has a SQ factorial symmetry. And so in fact, this is known as the Potts model with Q factorial colors. And so in that case, we can take the replica limits exactly. And it's actually very easy to do this, so I'll do it. You don't know this. At this point, I could just invoke literature on the Potts model, and it's very well known what the limit of the Potts model is when you take the number of colors to be 1. So here I want Q factorial goes to 1, so I want a 1-color Potts model. Okay, so that sounds weird, but it's very well known that it maps onto classical percolation. So I'm actually going to show this from this. It's very easy. So how do you see? So I want to take this replica limit, which is Q. I'm forgetting the boundary here. I want to take Q factorial goes to 1, okay, when you take the replica number to 0. Well, okay, so we have this partition function. So how do we do this? So what I'm going to do is expand the product. Okay, and I'm going to choose a graphical representations where wherever I pick this term, I'm going to draw a link on the lattice. And if I don't pick it, I'm not going to draw a link. Okay, so I have my square lattice. And so I expand this product, and whenever you pick this term, I'm going to draw this. And if you pick this one, I'm just going to leave that link empty. So let's say one of those terms could be something like that. Oh. So now every time I have a link, it means I picked this delta function. So I should say in the context of the Potts model, what I'm doing is known as Fortuyn-Castelline cluster expansion. Okay. So now you can, so each link has a weight 1 minus p. And if you don't have a link, you have a weight p. And now you can do the sum of the spins exactly. Because within each cluster, you have a delta function that tells you that all spins are the same. So now you do the sum of a spin. Okay, so you can actually do this sum of the spins exactly. So this gives you Q factorial per cluster. So for each cluster, you have all spins are forced to be the same. So this gives you this, okay? So this partition function you can rewrite exactly as a sum of the clusters where, okay, I have 1 minus p to the number of links I chose to occupied, p to the number of empty bonds, like empty links. Okay. And you have Q factorial weight per cluster. This is an exact rewriting of that partition function, which I should say, again, is very well known for the Potts model. I'm not doing anything new here. It's just. So, okay, so now the nice thing is in that representation, Q is just a parameter. And now I can take Q to be real. Okay. So it doesn't have to be an integer anymore. Here, obviously, it was an integer. Okay, so now this is like a high temperature expansion if you want. I'm summing over diagrams. Okay, so I have this sum of the clusters, and now Q I can just take to be a real number. So now I can take my replica limit, and I want this goes to 1. So this just goes away. So now you see your partition function is just sum of the clusters with a given probability to occupy the links, or in a given probability not to occupy them, which is also known as bond percolation. So that's the definition of what percolation is. You just put bonds with a given probability on links, and that's it. It has a trivial partition function, and but it has very non-trivial critical properties, and it has non-trivial critical exponents. So in particular, critical exponents are very well known from CFT work from the 80s and 90s. So I think nu is what, 4/3? Is that right? Yes, okay. So in particular, some critical exponents like the correlation length is this, and for example, the critical P here is 1/2. Well, that is. It's an exact result for percolation. So, and then I should say, of course, it is a CFT, and it has central charge 0. Okay, so it maps all the requirements that I said in general. So in that limit, for that very specific limit, d goes to infinity of this measurement transition, the stat-mech model ends up being a lot simpler, and it maps exactly onto percolation. Okay, so you can show here that this entanglement transition is just nothing but classical percolation. So it's kind of maybe physically appealing, and I should say there's actually one entropy which is S0, which always has that feature, and that was pointed out in the paper by Adam Nahum and collaborators. So it's percolation where you imagine like your entanglement is just given by doing a cut in your system, and again you notice like those probabilities are like making measurement or not. It's kind of like very appealing. You're saying like if you make any, you make many local measurements, and what matters is whether you like those measurements percolate or not, basically. Okay? So this gives you all critical exponents. So unfortunately, models in real life don't have d goes to infinity, and like people that do numerics, they do d equals 2, which is very much not infinity. And what they see is actually, so at least that PC is completely different. Okay, they see it near 0.2 in numerics. The critical exponents are actually quite close to percolation. Yes. Sarang and collaborators had a paper on this recently. But so the short answer is we don't really know what the transition is for finite d. Okay. So what about finite d? Okay, so instead of doing that d goes to infinity limit, so you can actually start from this because it's a limit you understand. Okay. So the problem is actually this enlarged symmetry. So the minute you include one of the d corrections, you actually break this symmetry down to this. Okay, so this is hard and still unknown. So you have ideas on how to do this. You should join the fun, and okay, you can add to the list of the many papers I had listed on this. Yes. Yes. No, I mean, so actually in the random tensor network paper, we also had a modification that gave percolation. So we just like made it up completely. That is, we just like decided to modify the Boltzmann weights and use this. It's something you do a lot in field theory. You try to modify it to understand the UV fixed point, and then you add a perturbation and see what happens. So we use this, but we don't have a physical context in which you get percolation. Yeah. Cool. So we're working on 3 things now. So then it becomes like thinking about like, transitions on KD trees type things. We're actually doing this now. I'm thinking about this, and there like the transition are more mean field like, of course, but like you can also think about what this gives you. So this is hard and still unknown. And also will, in terms of numerics, there's only so much you can do. If you're doing like measurements with hard random gates, you cannot do a lot more than 20 spins, probably even less. 20 is about right, what you can do. Okay, and in terms of field theory, what happens is you started from your Potts model, but you break it down to this SQ cross SQ. I should say SQ can be embedded in SQ factorial. It's known as Kelly theorem in group theory. Okay. So what it means is, okay, let me just write down like one thing, and then I'll move on to the. So if you have a field theory for the Potts model where you order parameter, I call it phi A. Okay. And it has this SQ factorial symmetry. You want to add like any perturbation that will preserve SQ cross SQ. So A runs from 1 to Q factorial. Okay. And so you can easily convince yourself that any perturbation of this type is going to work. So A and B, now you think of them as elements of SQ, and this is a class function again. So if that doesn't make sense, it's okay. It doesn't matter too much for the point I want to make. So the only thing I'm trying to say is, starting from the Potts or percolation fixed point, you can actually look at the perturbations, one over D, what they correspond to, and you can check that they are relevant. Okay, so this thing, you can compute its scaling dimension. So it's relevant in the RG sense. Okay, so what it means is, okay, I don't know what happened to this. Okay, so I started from that limit, I knew how to solve exactly, and the minute I go epsilon away, I get a relevant perturbation. And it takes me to something different in the infrared, and I have no idea what it is. Okay, yes. Yeah. Yes. Yes. Right, because the measurement also, they break unitarity, right? So every time you make a projective measurement, this is a non-unitary operation. So intuitively, that's maybe the way I would think about this. Even if you had a unitary circuit, any projective measurement is actually breaking unitarity entirely. But at the end of the day, you're like breaking unitarity in both. That's probably why they're like so similar. So I should say there's a slight difference between the two, which has to say with the number of replicas and a slightly different replica limit, but essentially they're the same. Okay. But yes, so that's the intuitive answer. So this is RG relevant at the percolation fixed point. And so what it means in practice is we have no idea what happens. Okay. So we can only understand these limits, and then you could try to do perturbation about it, and you find that it's relevant, and it flows to something else, and we don't know what happens. And so there's a big question mark, and no one really knows what the transition is at this point. Yes, yeah. Yes, it has to. So the C equals 0 is the only thing I know from this. Okay, so since the partition function is trivial, it has to be a C equals 0 CFT. Okay, but beyond this, I don't know what the critical exponents are. I don't know what nu is or whatever. Okay, so we don't know what type of, and it could be as hard as the plateau transition in the quantum Hall effect, like I said, and in which case we'll probably will never know, right? But okay, but there's at least one limit, as you saw, like there's some limits in which we can say some things. Okay? But it has central charge 0. But that gives you not that much information. It's like there's many non-trivial CFTs at C equals 0. All right, so that's all I wanted to say about the measurement and random tensor networks. So are there any questions about this before I move on to MBL?
But not
Yes. Mm-hmm.
only example of have a global.
Mm-hmm. Yeah.
So
yeah.
Is it possible that you're
Yeah, so originally we thought maybe there was like crossing through a mobility edge kind of thing or something. I don't know. So our original motivation for the random tensor networks was actually many-body localization, which I'm going to talk about now. But I think now, after the fact, it's pretty obvious this has nothing to do with the MBL transition. Okay, you know about the MBL transition, of course, but so I'll talk about this more now, but I think there's no relation. Going back to your question, could I think of this as like, Hamiltonian system? I don't know. I mean, there's no parent Hamiltonian here, right, in the way it's constructed, or it's not, yeah. Yeah.
I think that
Hmm?
is it states that
Yeah. Mm-hmm.
in the thought of as random
I don't know. My guess is I would say no, but like all I can tell you is that, yeah, I mean, this is definitely what happens, like say for measurement, depending on the rate of measurement, you will change the slope of the entanglement growth, for example. Will like grow with a different rate if you want, depending on how many measurements you make. Then if I can think of it as a excited state of some Hamiltonian with some conserved quantity, it sounds like far-fetched that this is possible too. But you see, I think of them as like something I get after dynamical time evolution in some way.
has all the right properties. I think
Mm-hmm.
mapping it short range mind.
Yeah. No, that is true. That is absolutely true. Yes. So that is absolutely correct. So yes, I just don't know how to do this. Let me rephrase this. I have no idea how to do it. Yeah. Right.
So measurement problem is
yes.
But if matrix
Mhm.
spectrum.
I don't think so. So you see the tensor network model also has a nonlinearity of some kind, is that you have to normalize the wave function at the end. You see the problem is like I had this divided by trace of rho to the end. It sounds innocent, but it means you don't get a naturally normalized wave function. So you have to normalize it before you compute entanglement, and so it means something. And the measurement problem, the reason it's nonlinear is also this, right? So you need to normalize your wave function every time. So that's the same issue in both. Anything else? All right, so if there's nothing else, I want to spend the last, 40 minutes, I guess? Let me say half hour on the MBL transition. Okay, so I won't be able to say as much, and I will be a bit more qualitative, but I want to tell you about what is it? Yes, okay, so I'll get there. But yes, I'm going to talk about what we think we know from renormalization group approaches, and you'll notice I'm using very careful wording. Okay? To leading order, what we know is 0. So there are some things we think we know. There's some emergent picture, but it's way less rigorous than everything I told you so far. So that's my second part, which is going to be a lot shorter, which is on the MBL transition. Okay, so that will connect naturally to what Maxime talked about yesterday. So this is, I'm going to emphasize this right away, a completely different beast. Everything I told you about so far. So again, from what just Maxime told you about yesterday, you can think of MBL, and that's the way I will think about this, as like you start from something trivial where you have a product state, and then you have some tiny or maybe a weak interaction on top of this, and you can rotate this to a basis where you have local conserved quantities. So that's which are called L bits or Lyons or local integral of motions, where you get, so they're usually called tau z's. And so I will just refer to Maxime's lectures yesterday. Okay. Okay. Where the tau z's are obtained by some quasi-local unitary rotation of your original Pauli matrices. Okay, so intuitively, you're starting from your spins, and they had product state, but you added all sorts of interaction. But you can define local conserved quantities which commute with your Hamiltonian. Okay. So your Hamiltonian is only expressed in terms of those tau z's. And those tau z's are local because they started from a local operator, and you acted with the, if you want, a finite quantum circuit, or like say a quasi-local unitary. Okay, so they have exponential tails, but they're local operators. Okay? So this is what MBL is, and this has SA. So that's what I will take as a definition of MBL, I should say. So this is what's known as full MBL. I have those local conserved quantities. So you have SA equals constant in the whole spectrum, so R yellow. And again, I'm doing 1D. And so this is a strong disorder, or this is in this MBL phase. And so the assumption is that, so I should say this is due by, okay, so this was done by Abanin and collaborators with Maxime and David Hughes and collaborators. And this was shown by Imbri in one specific model that you can do this at strong enough disorder. And so for me, this is going to be basically my definition of the MBL phase. I'm going to assume that if I can do this and define local conserved quantities like this is my MBL phase. But again, as a function of disorder, call it W, there's this transition where you have this MBL regime if disorder is strong enough, but if disorder is weak, you actually satisfy ETH. Okay, so there's actually some conjectures, I should say, even the question whether you have only a unique transition or more things in the middle is still people are debating. So I should say many things are like open, okay? But I personally believe there's only one transition here, but like, and so here S is again fixed by ETH, whereas here it's just constant. And again, my question is, what is going on here? Okay, so that's the question of the MBL transition. I don't want to think about the phases. I actually want to think about what is the transition. Is there any critical exponents in the same way and so on? Is there anything universal? Okay. So I should say there are many papers on this, and clearly I'm not all going to list them on the blackboard. Okay, many works from people in the audience. There are many numerical works. So if you do numerics, the problem is you're limited to about 20 spins. Okay, so because you have to essentially diagonalize the many-body Hamiltonian. Okay, so you can only do this exactly for like about 20 or 22, 24 spins. Okay, and you need to get eigenstates, or if you do like say TBD or things like this, or TDMRG, you limit it in finite time, and you also have issues. Okay. In an experiment, so there are also, I should say, there are several experimental setups that claim to have realized this, but you also limit it in finite time. You get finite time features, and then at some point, some atoms will lose your optical trap, and you have to stop. Okay. So one approach that has been, well, okay, people tried, including myself, is to try to come up with like what I would call toy models or phenomenological models that will hopefully capture what this transition is about, okay? And to try to solve them and to learn from them. And so I've listed here on the board, probably not exhaustive, but almost, okay? So it has many of those called RG papers, okay? Which RG meaning renormalization group, so it's meant in a way that's clearly more phenomenological than what's known for field theory and so on. They have RG like flavors to them. They're like decimation schemes, but you can call them usually people like the word phenomenological RG. In other words, they're kind of toy models, or they're kind of based on like some strong assumptions, which you have to check or not, okay? And they're based on some phenomenology that we believe is true in both phases, okay? So I'll try to tell you a bit about this. And so there's a relatively long list of papers, and obviously I'm not going to go through all of them and tell you what it did differently. I'm going to try to tell you about basically like the second half here that started by this paper by François, Wojciech, and collaborators that uses the idea of avalanches. So that's what I will talk about. So I will explain what this is. Okay, that the idea that the transition is driven by avalanches. And so this led to something, so in those papers, to some picture of the transition that can be formulated as something which is similar to a Kostelis-Thales-like transition. So it's a BKT-like, if you want. Okay, and my goal for the last like half hour of this lecture is to tell you a bit about how that comes about, okay? So I'll try to tell you there's a BKT type structure, okay, as in superfluids and XY model of this transition. Okay? And so this came from those papers, and I was building a lot on this very nice paper on avalanches. And so I'll try to convince you this is a reasonable physical picture for what's going on at the transition, okay? And if you want to know more, you can have a look at those papers, okay? So I should say some of those RGs are like very phenomenological, but they're also very complicated. You have to solve them numerically. Some of them, you make them so simple, you can solve them analytically, but then you have to question whether they actually describe the transition. Okay, so it's really, you try to model things to some extent. So for example, this one here, the one with Maxime, is exactly solvable. Okay, so if you like exactly solvable stuff, you can just have a look at it. It is described by a KT transition, but then there's a question of whether it actually describes the MBL transition. This one is kind of exactly solvable too, and this one as well. Okay? The other ones you have to kind of solve numerically in some way. Yes. Yes, so they based, absolutely, so that's where I was going to go. So, okay, so there's one message. So, of course, contrary to, you go, what do we know for sure? Not a lot. Okay, so because it's a hard problem. Okay, so you have to make very strong assumptions one way or another to get results. Okay, so originally the first ones were based on like some rules that we thought were reasonable, and some of them, you know, aged better than others, like in terms of like whether they made sense. Okay. But with time, many of those are kind of converging, which is kind of a nice thing. They could be very different, but they somewhat, I will try to argue they kind of produce a similar picture at least, okay? Maybe Wojciech will disagree and we can argue, okay? But, okay, so they kind of produce similar things, okay? So what do we know? Again, I want to be clear that since this is a lecture, here I'm actually going to lecture about stuff I'm like not 100% sure about, okay? So this is only based on thinking about this problem a lot, but we're still learning, okay? And there's a nice physical picture that's slowly emerging of how the transition is happening in terms of avalanches. And basically it emerged from many things, a combination of numerics, so ED and like TBD and things like this, plus some physical intuition and new ideas. Okay, so there's a lot of this. Some phenomenology if you want. And plus some like simple toy or phenomenological RGs. So that's pretty much where we're at. Okay, so I understand this is, it's not like I'm going to be able to start from this problem and map it onto something exact and then solve it for you. Okay, so this won't happen. So you have to make some relatively strong assumptions and to try to see what's going on here. Okay, so one thing I do want to emphasize is there is a dramatic difference. So this is going back to a question that François asked. Okay, so here there's one dramatic difference with the other type of transition I was telling you about, that in this phase by ETH, entanglement has to be log2 times LA. You don't have a choice about the log2. Okay, this is fixed by ETH. So this cannot move continuously or in any way. Okay, so meaning this is entirely fixed by ETH. So you not only have volume law entanglement, but you have maximally entangled thing all the way to the transition here. And it turns out to be actually a crucial difference, which is the first weird thing about the transition I want to talk about. Okay. Because so originally, people wanted to think about, entanglement looks like an order parameter type thing for this transition. And so you could think that maybe SA of LA was like a local observable in an ordinary phase transition, right? So what does that mean? Well, let's say you have a normal phase transition and you look at the local observable. Okay. So usually the way it works, if you have a second order phase transition and you have a correlation length, if you look at scales less than the correlation length, you see the critical point. And if you look at lengths larger than the correlation length, you start seeing whether you're in one phase or another. Okay. And so you could assume that you have this scaling, and this is what Tarun Grover did back some time ago. It was in 2014. Okay. So you can assume you have an ordinary second order phase transition. And so as a function of LA, let's say you have a correlation length, and that's my LA. Okay. So here, if LA, so let's say you're on the ETH side. Okay. So if you have a correlation length and you look at LA much larger than this correlation length, you should see that you ETH. Okay, and so we have SA equals log2 LA. And now if you look at scale less than psi, normally you should see the physics of the critical point. Okay. So here it should be the phase, you see the phase, but here you should see critical physics, right? If your scale is less than the correlation length. But now if LA is, okay, LA much less than psi, but the point is that by ETH, SA is still log2 log LA. Okay, so if you take an interval, even if you shrink it to a lattice scale, you take one side. Okay? ETH is always going to tell you, entanglement is log2. It doesn't care if you went all the way to the lattice scale. So from this, you see this seems to suggest that, in other words, if you want, you have S as a function of L. And by ETH, I know it's a straight line with coefficient log2. But if it were a normal phase transition, you see it doesn't, it has maybe a psi here, nothing happened. Okay. So from this, Tarun deduced that, the critical point must surely be entirely thermal with maximal entanglement. So Tarun actually did this a bit more rigorously than I'm doing it. He was using strong subadditivity, but the result is the same. Okay. So this looks like the critical point from this. Okay, is thermal, and basically maximally thermal, right? So it's like in the ETH phase. All right, so it turns out, I think most of us believe this is not correct. Okay, so actually, if anything, we think the critical point is actually entirely localized. Okay. So this makes very little sense physically. So it would tell you, if your critical point is localized, this would tell you on the MBL side, you look at small scales and you see ETH physics. And then suddenly you increase your system size enough that you start thinking, oh, in the end you're localized. So in the way we actually think about the transition in all those models, and what numerical evidence also strongly suggests, is if anything, it's really the complete opposite. And the critical point is more an instability of the MBL phase. So the MBL phase is extremely fragile. And you need very little to just make it thermalize. Okay. So basically what this tells you from the argument is that entanglement doesn't scale like a normal phase transition here. It doesn't scale as a nice local observable in the second order phase transition. And if anything, it actually has a jump, right? So that's what ETH is telling you. So actually the current belief, and I think this is anyone working on this transition agrees with that, as far as I know at least, the critical point is localized. And it's actually 100% localized, okay? So it's actually 100% in the other phase. And it has actually, okay, RELO entanglement, so that is maybe more debatable, so I won't write this, okay? And so in particular, if you look at SA over LA at the transition, it actually has a jump. So if you look at W, what this does, it's actually fixed to be log2, the ETH phase, and then it jumps. Something, okay, LA is not necessarily infinity here, but there's basically a jump at the transition. Okay, so it's one first slightly unusual feature about this transition is that, and if you want, let me emphasize why this is weird, right? So we're talking about something like thermalization, and the important point is that even if you take a tiny system, even if it's one spin, you already know your full system is thermal, right? You don't need to look at a big system and scale things and whatever, right? So if your full system is acting as a bath, or if you have entanglement, it's highly non-local, right? So if you measure, you can already tell from looking at a few spins whether your full system is thermal or not, right? So this is something that already tells you this transition is kind of unusual. So SA over LA jumps at the transition, and this was first pointed out, a paper by Vedika Kemani and collaborators, David Hughes and Donna Cheng. There's also a paper by Brian Clark and al, and also a paper by, also in that paper with Philippe Dumitrescu and myself, this one. Here, Oh yeah, I didn't take LA to infinity. Okay, so if I take LA big, this is also actually going to jump by log 2. Yes, LA is not necessary. LA could be 3 here. Okay. But if LA is large, this is indeed going to actually jump by log 2, which will turn out to be universal. So at the time when people thought about this, it looks like there are some aspects of that transition that look first order-ish. Right? So there's like jumps and discontinuities. But on the other hand, there's also some other quantities that look very second order. Okay. And so part of the resolution, what is one consistent scenario where things seem to make sense is this KT scaling that I will try to sketch for you. Not too long. Okay. Now, I'll try to do this briefly. And again, if you want to know more about this, you can have a look at those papers, and particularly the last one, wrote a detailed version of this. Okay. So this starts with a simple mechanism for the transition that was proposed by Wojciech and François. Okay. Forgot the date of your paper, but okay. Something about, okay, which is not as avalanches, which is a mechanism of instability of MBL, and this is also what they use to argue that MBL could be unstable in dimension larger than 1. It could be only stable. So let me sketch how this argument goes. It's actually relatively simple. So the idea is the following. So let's say you have a nice MBL system. So you have those L bits, or local conserved quantities, like they're being up or down. And now you imagine that you couple this to a region where you imagine you're completely thermal. Okay. So why does that matter? So you have disorder, which means you'll have rare effects, okay, which means you will always have, even if your disorder is strong, you'll have regions where your disorder will be accidentally weak and could be on the wrong side of the transition. Okay, so it's always crucial to, in disordered system, to think about the role of those rare regions. So here you think of a rare ETH region, and actually I'm going to model it as a random matrix even. Okay, but it could just satisfy ETH. So this is a 1D region, and this is supposed to model a rare ergodic region, which again is unavoidable just from rare event physics, right? So it's exponentially rare to have a big thermal region, okay, but it will happen. You have a big enough system. So, okay, and so the question is, what is the role? Let's say you were unlucky and you got like a big thermal region. What is that thermal region going to do to your localized system? Is it, yes? Yeah, so this is supposed to, I'm modeling here my system in real space. So I'm imagining there's a region of space where, you know, definitely I was not MBL. I was like deep in the ETH phase, and I'm just replacing this by a random matrix. I'm saying it satisfies ETH. All my eigenstates are kind of random. And here there's a nice region where I could just do this rotate to the L bits, and you couple the two. Okay. Yeah, so what remains is you see this random, this ergodic bubble. So yeah, what François called this an ergodic bubble. Okay. So this matrix element is going to decay exponentially, right? That's localized physics to all the localized spins. Okay. And so now what you want to ask is, let's say, so this is, I should say, this is a finite number of spins. Okay. This is not like a continuous bus or anything. It has like a finite level spacing. And it has initial size like n naught spins, so its level spacing is like 2 to the minus n naught, okay? But it's finite. So now you ask, let's say this thermal bubble is going to thermalize the first spin. Okay, almost surely this will happen if this is a big enough ergodic thing. So it will be enough to flip this spin and thermalize it. And so, okay, so the naive thing you could say is now you like reabsorb this in the bath. You call this, you have a bigger bath with one more spin. And you want to ask if you can keep going and absorb the next one and the next one and the next one. Okay. So every time you absorb a spin, your level spacing goes down by a factor of 2. You get even more smaller level spacing in your bath. Okay, so naively, you could say that once you thermalize this, you only have to pay a matrix element of this price to do this. So if you do this, you get that it will always eat up the whole system, and that's obviously nonsense. So, however, you should realize that the L bits don't have like tau plus, tau minus between them. So if you thermalize this L bit, this doesn't help you flip this one. You always need to pay this matrix element that decays exponentially. Okay. So the setup is the following. So you imagine that your bubble is big enough to absorb like all those spins. Okay. And then you ask whether it can thermalize this one. So that's a slight oversimplification of what of this argument, but it captures the essential physics. So you ask about the matrix element. So this matrix element to flip this spin goes as x to the, you have this exponential factor, and you also have a term that comes from ETH physics or random matrix theory, which is 1 over square root dimension of the Hilbert space of the bubble plus those x spins that you absorbed. Okay. So dimension of Hilbert space here is 2 to the n naught plus the number of spins you absorbed, x. So it's a matrix element for flipping this L bit. So it's a matrix element from your random matrix. It's like flipping this spin. This is something that couples your random matrix and the L bit and wants to flip it. Effectively, if you want, I'm computing a Fermi golden rule rate for flipping this spin. So this is just the general scaling of this. And effectively, you should compare this to the level spacing of your bubble, which goes as 1 over dimension of the Hilbert space, which is 2 to the minus n naught plus x. So effectively, what tells you whether like the thermal bubble is going to keep growing and thermalize the whole system, which is what François and Wojciech called an avalanche, okay, is you see you have two competing exponentials. You have this that decays exponentially, and you have also this that decays exponentially with x. So if you do the same in higher D, you can easily convince yourself that the matrix element is always going to be larger than delta, which is what led to this idea that MBL could not exist in dimension larger than 1. Okay, but in 1D, you see that there's if you define this, which is what also Maxime talked about yesterday, it's a ratio of matrix element over level spacing, which basically tells you whether this is larger than 1, you'll want to thermalize things, but if it's much less than 1, you can say you're still going to be like nice and perturbative. Okay, this has a critical threshold, okay, as a function of x. You have two exponentials competing with each other. Okay. So we can see this easily here. It's exponential minus xi divided by xc, and we'll have square roots of dimension of Hilbert space. So that's log2 over 2. Okay, so you see this is a function of x. When x becomes big, you have clearly a critical value. You have a negative exponential and a positive term here. So if psi is larger than a critical value, say critical, which here happens to be 2 over log2, but if you had like two sides, okay, if you had like spins on the other side, you would just get log2. So this means that the interactions are not decaying strong enough, and you will thermalize the whole system, and you'll get an avalanche. And if psi is less than this critical value, this process will stop. Okay. So, all right, so this is the first time I saw this argument, I was very skeptical. It sounds sounds kind of counterintuitive that only one thermal region should be enough to thermalize a whole chain of like Anderson insulator of MBL system, right? I should say there's clearly a very strong assumption here, or at least there's one clear assumption, which is as you absorb all those localized bits, I'm still dealing with my enlarged bath as a big random matrix. I'm still assuming it's completely featureless. It doesn't have any feature. The matrix element is purely given by ETH. And there's no structure to the spectral function of this or anything, right? So I'm just modeling this as one big thermal bubble, okay? So, but nevertheless, there is some numerical evidence, although, okay, we can discuss whether that's true or not, that this works very well. Okay. Yes? For the form of the matrix element. So like this 1/square root dimension Hilbert space is basically assuming eigensets are random, or it's a random matrix result, right? It's, well, and if you had more substructure in all the spectrum, I mean, okay, the criterion of whether you can thermalize a spin or not would be more involved than this. You would have to look into the details. Okay, so so basically what this is telling you is if you have a rare region that's big enough, and that will always happen with some probability if you have a big enough system, if your decay of interactions like this thing, which we could call a localization length, is too big, you're just going to thermalize the whole system. Okay? So naively from this, it could suggest that maybe the picture is you just get a transition wherever this will depend on disorder, and maybe you just tune disorder and you reach that critical value and then you avalanche, and that gives you the transition. Okay? So this is almost correct. So the only ingredient that is missing and is captured by all those RGs I'm talking about. So in MBL systems, this effective psi is something which is, if you want, renormalized. So there's like a bare value which comes from, say, the single particle correlation length if you started from 3 fermions. But the psi is something that, if you want to define any type of RG flow, is flowing. So let me give you just a picture of what this looks like. If you have, like, say, a thermal region here, okay, and you ask about its matrix element to flip spins over there. But let's say now in the middle, I have another tiny ETH region. Okay. And you want to ask about the effective matrix element to do this, to flip a spin over there. Basically, this decay, okay, so, is going to depend on the density of those thermal bubbles in the middle. It's not just the bare localization length, and it's something effective, if you want, which will depend on the density of those thermal regions in between. Okay, so there's various models to do this, and this is actually what I'm not going to get into, but this is what those RGs are doing, is actually try to do, they incorporate this in more or less explicit ways. Okay, so now let me try to kind of draw an artistic view of an RG flow on this, and I realize I'm being pretty vague because I haven't really introduced any RG at this point. Okay, so you can just trust me that some of these can really reproduce this exactly. So think of the renormalization scale as something where you coarse grain on bigger and bigger scales, and effectively you incorporate bigger and resonances at finer and finer level spacing. Okay. So what happens is the following. So you have two parameters. So that's the proposed, at least, scaling theory that we're suggesting. So one parameter is this localization length. Okay, I don't want to. This length which characterizes the decay of typical matrix elements. Let me be more precise. Okay, and there's a critical value. Okay, as from this avalanche, okay, which happens to be log2. It goes from both sides. Okay, and so here, if you here, like, you have MBL, and if you here your avalanche, okay, and any rare region will destroy you. So now the other parameter is the density of those thermal regions. And like I told you, this density of thermal region is also renormalizing this. And so in particular, this effective psi is actually only growing under RG. That is, as you discover more and more resonances, this effective psi only keeps increasing. So from this, okay, so again, it's only cartoon at this point. What ends up happening is a picture that looks like this. Let me comment and okay, kind of see where I'm going with this KT physics. Okay, So what I'm drawing here is the following. So if you're here, what happens is your effective psi is increasing because just you normalize, you found some resonances and your effective psi of typical matrix element is increasing, but you're well below this threshold of avalanching. And so you remain nice in MBL. And so you have this line of fixed point where you, at the end of your RG procedure, you just diagonalize your full system and you form del bits. So however, at this point here, okay, what happens is you think your MBL, but effectively this zeta, is renormalized, and it goes beyond this avalanche value, where then you're like past this instability that tells you you should get an avalanche and your full system is dead and you just get thermalization. So from here you see it's really, so from this picture it's not fully clear what I mean by KT physics. You can write down RG equations, and again for some of those RG models, like you could, yes, so I can write down RG equations if you want, like I will, so you get them explicitly in that one, so that's in that paper with Maxime and Anya Koemikina. We just had an RG model where you get this exactly and you can write this down. Okay, I'm just giving you a hand-wavy picture of what is going on. So in terms of RG equations, this looks like this. You have beta dl minus 1 minus the constant rho minus 1 and the density of resonances over dl another constant minus c. Okay, so this equation tells you that basically thermal regions are relevant or irrelevant based on this avalanche criterion. And this tells you that zeta is renormalized by thermal regions and only increases. Okay, so those are only like leading order RGs, so you can argue them on phenomenological grounds, or in some cases, again, we can derive them exactly. Okay, and so those are BKT type transitions. If you zoom in like around that region, this looks like a KT transition. And so this is kind of appealing in some way. It tells you that MBL is, it's a perturbative construction, right? You construct those L bits. And this tells you about the response to something non-perturbative, which are those thermal regions. In that region, they are irrelevant. Whereas here, they're relevant, and if they're relevant, they destroy you, and you get thermalization, and you get this avalanche. Okay? However, it just doesn't happen as a first-order phase transition as you go through this, because this effective zeta is just renormalized as you coarse grain or as you have your thermalization process. Okay. And so let me just finish by saying that this has various consequences. In particular, sure. No, it will, yes. Well, I mean, sure, I will show you. Yeah, sure. I mean, this is a KT flow equation, right? Like, I mean, I can show you afterwards if you want, but yes, this is a KT flow equation. Like, so this tells you in particular that you see this like matrix element decay length is something which is finite at the transition. It's absolutely not blowing up, okay? So this length is entirely finite at the transition, and it actually has a singularity, like a square root singularity, which comes from KT physics. So this is the analog of the stiffness in KT transition, and this value is universal, and it's log 2, and it's just set by the level spacing. Okay? So near this transition, if you were able to actually measure how the matrix elements decay, okay, it tells you that at the transition you have exactly this log 2 with this square root singularity. Okay? So there are various things you can compute from this. You can compute the distribution of the length of those thermal regions. They end up being algebraically distributed. And you can try to see if all those RGs numerically give you something consistent with that picture. And I claim most of them do, and they seem to be consistent with that picture. Okay? So I realize, of course, this was a lot more hand-wavy than the first part. Again, if you want to know more detail, you can have a look at this or ask me a question. And with this, I will just wrap up. Yeah.
Thanks a lot. Is there any question?
Yeah, that's SA divided by LA. Yeah, no, so this is a limit where I took the thermodynamic limit, right? So it's finite LA, but I took an infinite system. That's the key point, though. Otherwise, it would be smooth, of course, like if I have a finite system. But in the thermodynamic limit, this quantity has this jump. Okay, so if you plot it, like if LA is like 5 sites, but I took the thermodynamic limit, on one side it's fixed by ETH, and on the MBL side it just jumps to something that's higher low. And if you take LA bigger and bigger, of course, this is going to go smaller. Does that clarify things? So this is, yeah. Yeah.
Think of that as a
Oh, are you asking, do you want to think? I mean, like the question was, is this a local quantity which is like an order parameter and is at the transition, and clearly it jumps, so okay. Depends on what, I mean, there's no free energy here, or like I don't want to, yeah, first or second derivative, I don't know. But if I want to think of this as a local order parameter, clearly it's jumping. So it suggests something more first order.
So you mentioned that this length is finite as a transition, but there should be a divergent length, I'm pretty sure.
Oh, yeah, there is.
If you approach the transition from the delocalized side, so basically if you ask a question, how big should be the system near the transition to see that it's actually delocalized ergodic? So does it diverge as in BKT also?
It does, yeah, yes, it does. So it has this like, yeah.
Okay.
So there is a length like this that just pops out of those RG equations in the same way it does as BKT.
Okay, and another question. What are conclusions for transport quantities out of this picture?
Okay, so
again, if I must say on delocalized sites near the transition.
So, okay, in terms of transports, I would have to like, okay, talk about, this Griffiths picture and subdiffusion and like rare inclusions. You don't really need this for here. Like I mostly talked about stability on the thermal, on the MBL side. So this picture, if you want, doesn't tell you anything new that we didn't know before about transport in the thermal side.
But does it produce the same, say, will it produce, say, subdiffusion with this change in X?
Oh, yeah, it will produce subdiffusion with a Z that goes as Xi. Okay, so that's maybe the only thing is like the dynamical exponent, if you want, will diverge quicker because of this. Like from the Griffiths picture, you get, the dynamical exponent blows up at the transition. So you have Z equals infinity at the transition, and it blows up faster. But it blows up as this length, this one. But otherwise, it's the same picture.
what is the some point
So
some point at least
oh, but not in correlation. Okay, so all right, maybe we should do this offline, no rather. But like, okay, so okay, but yes, so there are questions even in that picture. Some of those RGs actually predict an intermediate type phase that's in the distribution of the length of the clusters, but that's way more refined structure. But yes, let's talk about this offline. I think, yeah. Oh, this reference? Sure. I mean, okay. Anyone has like archive? So just can anyone Google? Anyone, Maxime or something like? Okay, Maxime, can you find the reference for me? So can you find the paper with Philip, the last PRB? Okay. Any other question while I do this?
Okay, maybe we can thank Romain, right, and reconvene at 2:30. Yes.
Yes. Yeah. Thanks.